All right. Good evening, ladies and gentlemen. My name is Alan Forget, and today I'm going to talk to you about my summer work that I've done with Professor Jordan Kyriakidis on the Casimir effect at finite temperature and zero absorption frequency. So, I will first start by introducing you to the Casimir effect, kind of show you where it comes from, how is it, sort of give a gist of how it's derived. Then I'm going to show you how Lifshitz came in and contributed to the Casimir effect, and show you his grand equation. And we're going to look at that equation by making some approximations, specifically two kind of approximations, what we call the high temperature and lower temperature approximations that I'll explain during the talk. Then I'm going to show you some nice plots, and then I'm going to summarize and thank some people. So, let's start. In 1948, Henrik Casimir has found that if you have two infinitely long, perfectly conducting plates separated by a distance L apart, you get a force per unit area given by this equation. And notice that the force is inversely proportional to the separation to the fourth power. And this force has been measured in 1997 by Lamoureux to within 5% uncertainty. So we do believe that this equation has some truth. Now, the way that Casimir derived it in his original paper is something about van der Waals forces. I'm going to take a different approach, and this to use the one thing that quantum professors love, and that's the harmonic oscillator. As we know from quantum, the energy of the harmonic oscillator is given by as follows. But what's more important is if you set n equals 0, if you look at the ground state, it's still a finite energy. Now, if you have a photon in a box, or any kind of wave in a box, you can describe the electromagnetic field essentially as a collection of harmonic oscillators. And the n in this case will represent the number of photons you have. But what if you set n equals 0? That would mean you don't have photons, it'd be a vacuum. But there's still energy given right here. What's so significant about that energy? Well, I'm glad you asked. This is where we get to the Casimir effect. So these black lines represent my plates, and their separation is L. Between the plates in the x direction, these vacuum modes can only take discrete values because of the constraints given by the plates. Whereas outside the plates, there's no constriction. It can take any value at once. So between the plates, there are less frequency modes than there are outside, so there's less vacuum fluctuations. And these vacuum fluctuations push on the plates. But if there's less here than there are here, there's a bigger push outside than there are inside, and that's what makes the plates come together. The best analogy I can give you is to think about two boats in calm water. Even in calm water, there's some ripples, and between the boats there are less ripples than outside, and the outside ripples push harder than inside, and that's what gets the boats coming together. Now, Lifshitz came along and said, your results are great, but we need to generalize a little bit. Specifically, he assumed now that the plates were not perfect conductors, but they depended on a function of the permittivity, which is a function of the frequency. And he also considered temperature. And his work can be found in this book, in the Landau-Lifshitz series. I'll just simply give you the result he got. This is the force given in terms of the length, the separation between the plates, and the temperature. And to do that, you have to evaluate the frequencies along the imaginary axes. And I've defined some constants. I define the S as follows. And these zetas are, of course, the imaginary frequencies. And the P is just a variable of integration. Nothing interesting about that. But for the purpose of my summer research, I only looked at the case where all length scales, not just the length between the plates, but all length scales are much, much larger than the characteristic absorption frequencies. In that case, we can replace the permittivity just by a constant. More specifically, its value at frequency 0. not to be confused with the permittivity of free space. In that case, I first define, just for convenience, I define what I call a thermal length to be that, but most important is that it's inversely proportional to the temperature. And then I then define this thing I call the length ratio, that be just the length divided by the thermal length. And when you do that, the force can be simplified by this equation, which is a bunch of prefactors, times 1 over the length ratio cubed, times this thing I just call I, where I is defined as follows. So whenever I say I in the presentation, I mean this equation. Now, even this equation, it's not very clear how the force is related to the temperature and the length. So, to make that more clear, I've decided to try to use the Euler-Maclaurin summation formula. If you take that formula and apply it in this case, you can rewrite I as these terms. And here's the interesting part. If you look at each term, which I given these two a name, I call this one the high temperature regime and the low temperature regime. And each regime is significant depending on the size on the length ratio. So let's look at each case individually. Let's start with the low temperature regime, which is when the length ratio is much, much smaller than 1. In this case, you get that. But what's important is not the integral itself, but the fact that the integral has no dependence on the length ratio. All the dependence on the length ratio comes outside here. The only thing that the integral depends on is the permittivity at 0 frequency. So you can immediately conclude that the I is inversely proportional to the length ratio, which then that implies, if you plug that into the original equation, that the force is inversely proportional to the fourth power of the length, and it's independent, and it's also independent on temperature. That's pretty much what Casimir got, except it looks more simpler than that. But if you set the epsilon to be infinite, you do get Casimir's result. But here's where things get interesting. If now the length ratio is much, much larger than 1, then you look at that other term, which I call the high temperature term. And in this case, there is no L sub r anywhere in this equation. This I is independent of L sub r, which means therefore that in this case the force must be proportional to the inverse cubed power of the length, and it's proportional to the temperature. And just for shits and giggles, I took the epsilon to be infinite, and that's what you get. So we have something interesting. If the length ratio is very, very small, much, much smaller than 1, the force goes over the -4th power of the separation. But in the other inequality, in the other direction, it goes as the inverse cube. So when the length ratio is within order of magnitude 1, what happens? Does it do some crazy stuff going on? I don't know. So I decided to take an analytical approach on this. I decided to plot this equation that you've seen earlier, and voila! So you can see, so here's the x-axis, the thermal length, not the thermal length, the length ratio, and the y-axis you've got the sum of the integral term, that I. And I evaluate for different permittivities. You can see up here that it looks like a slope of -1. And here it looks like a constant, which seems consistent with what I've shown you before. But if you look very carefully, there's sort of a weird dip going down here, especially in the case where epsilon gets close to infinity. The next plot emphasizes this a bit more. What I did is I drew the line for, I plot just the high temperature regime only. Oh, I should mention that this is only the case where epsilon is infinite. It's the same thing for any other value of epsilon, which is near infinite. You can see clearly here that it dips. Personally, I thought it would have gone, the black line should have gone like something like this. It sounded more intuitive. I would have never thought it dips down like this and then levels off this way. So it was pretty interesting when I saw that. So in summary, Casimir got that the force per unit area between the plates falls off as 1 over the 4th power. But then Lifshitz says, yeah, that's true, as long as the length ratio is much, much less than 1. If the length ratio is much, much greater than 1, the force actually goes over the inverse cube. And there's also a temperature term. And if the length ratio is about 1, well, there's not really a very simple analytical way to explain it, so you refer to the plot. To conclude, I want to say like a couple of words on what's the point of all this. And it simply is to get us aware of the fact that even when the temperature is finite, and even when things are not perfectly conducting or almost conducting, you can still have these weird vacuum forces between two little things. So if you want to build like nanotechnology stuff, you have to take this into account. Now, I've only considered the case of infinite planes, but as future projects, I could have also considered different kinds of geometries. And I've even heard that sometimes the forces are even repulsive. So, I'd like to thank a few people. I'd first like to thank my supervisor, Professor Jorn Kierkegaard, for the wonderful opportunity of conducting the research. I'd also like to thank Professor Wally Geldart for a lot of advice about my work. I'd also like to thank the rest of the Kierkegaard group for their advice and a lot of hints helping me out with my code. I'd like to thank Dalhousie University for the opportunity of coming here. And finally, I'd like to thank all of you for coming and listening to my presentation. Thank you very much.
Thank you. That certainly got my energy up. So, any questions for Adam?
So if you go back to the slide where you have taking the permittivity to infinity, where you have a finite temperature expression for the force that's universe power. Sorry, the next slide.
Oh, you mean
the theta 3, not the one before plot. And then, yeah, that one.
Okay.
Okay, so there's an F infinity and it has a linear temperature dependence with the L3 in bond. So if I take temperature to infinity, this force just blows up, and that's the calculus. So how do you explain that, interpret that? Is that an entropic classical force?
So this?
Yeah, that.
So you're saying when the temperature goes to infinity?
Yeah.
I'm not entirely sure. I think what's going on is because the temperature is finite, you're not dealing with necessarily zero. They're not dealing with zero fluctuations. There might be some photons actually appearing there, and they could cause greater forces. And when you set the temperature to be infinite, I think that's the answer. I don't want to be 100% certain, but does that answer your question?
It might be a bit simplistic, but the temperature of what? Temperature of the vacuum or the?
Everything. I'm assuming everything has the same temperature, so even the vacuum.
Is that set like the density of states in your vacuum fluctuations? Is that what it does, or?
Yeah, it's just the overall temperature.
Okay.
Any question?
Yeah, so you mentioned electronics at the end.
Yes.
So I'm just wondering, so if you have like an electronic device, like, you know, however big they are, I wonder
How small?
like how much is the Casimir force going to be, or like at what scales?
Okay, yeah. I looked it up in the presentation, but going back to this equation, let's just look at the, actually I can do this. Looking back at like this equation just for simplicity, because of the prefactors, you can show that for a force to be like within order of magnitude of say 1 Newton per square meter, the length scale have to be 1/10 of a micron. So they have to be very close to each other. But the reason why I'm saying that it's important is because, you know, electronic devices are getting smaller and smaller. I'm assuming at some point that it will become significant.
Any more questions? Thank you, Adam.
Thank you.